and it's actually it's actually a mathematical lower bound that all sorting algorithms based on comparisons can achieve no better than order n log n average performance. Right, that's a mathematical lower bound. Then from now on we are talking about something different. For instance, this one, the counting sort can be only applied in the situation when we are sorting things in specific slots. Like for instance, I'm telling you that you are going to sort something in between 1 and 10, right? I already told you it's between 1 and 10. For instance, we have something like this, right? So if we are sorting something like this, actually we have special techniques that are not based on comparisons between two elements, but we can use use space. If we open up a space of 10 slots, okay, make it 6 slots. This one, the index 0, 1, 2, 3, 4, 5, 6. Then we can 1. Then here's 1, 3, 2, update to be 2, 6. So actually, this array can be organized in this way. And then after counting, we can sort them as the first one is 1, the second one is 2, the third one is 2, the fourth one is 3, and the last one is 6. Cool. So this algorithm is called the counting sort, and it's not based on a comparison between the elements. It's especially useful when the when the value domain of the values are limited to some range of integers. For instance, in some programming problem sets that you may be getting from your homework problem sets, you may get some problems like this. So sort 100,000 numbers, which each of the values are in between 0 and 100. Right? So if you're having these situations, then if you are using these algorithms to sort these 100,000 numbers, you are going to have at most 100,000 times log 100,000. But if you are using this counting sort, you actually only need to put everything into this array and then go past of 100. That's easy, and then the average performance will be very cool, and it becomes order n. And this n comes from either one is greater between this one and this one. Cool. That's the so we also call it one of the typical linear time sorting algorithms. And then for the best performance, of course, we cannot have anything better than order n. Then for the worst case, it's order n. Cool. So great. And then cool. And then we also cover one sorting algorithm called the radix algorithm. We won't cover it into much detail, but we just want to mention it. This one is pretty special. It's actually sorting by comparing each digit, each binary digit of the numbers. For instance, if for number 5, it's actually 1, 0, 1, 2, 3, 1, 1, 1, 2. Right. So if we are comparing 5 and 3, the radix sort, I actually first compare the last digit, 1 and 1. Okay, I'll use another 4. 4 is 1, 1, 1, 0, 0. Right. So in the radix sort, in the first pass, they only compare the last digit. So 0 is less than 1, so it will be 4, 5, 3, because it's 0, 1, 1. In the second pass, it compares the last two binary digits. Then 0, 0 is less, so it becomes 4. This one is 5. This one is 3. And in the third pass, it compares the last 3 digits. Then it becomes 3, 4, 5. Noticing that, because for the last 2 digits, 4 is already less than 5. So when we are updating, then 4 and 5 are actually keeping their original suborders. So in the radix sort, the time complexity is very tricky. So usually we call them to be order n. But being more precisely, it should be called of order n times k, where k is a constant representing the how many binary digits you have in your in your input scale. For instance, if you are having the 32 bits integer as input, then this k will be 32. And someone may ask that, so is it called order n or order nk? Because k is a constant, so we usually call it nk. But noting that if we are only considering the 32-digit integers, log n will be guaranteed to be less than 32. Right? So actually, n times k is even greater than n log n. That is the case when we are having very large, numbers in front as the coefficients. Then sometimes order n is performs even worse than the order n log n algorithms. But that's the algorithm. And when the k is very small, say k is 8 or 16, maybe it performs better. I don't know, but it depends on the scenario you are using it. Okay, then also the best performance and worst performance are also order n. Cool. These are the two algorithms we covered, which is called the linear time complexity. So if you can remember that, this is our fourth class in the sorting algorithms. We covered the first three in the first lecture. We covered the second set of three in the second lecture. And we cover these two in the third lecture. Okay. So this class is the review of these algorithms. But some of you may think that it will be too boring if we are just reviewing the old algorithm but not learning anything new. So I will introduce very briefly one of the new algorithms. It's called the shell sort. Shell sort, and actually you don't have to remember or implement this algorithm just for you to know. And just later I will use a video to show you how this algorithm differs from each other, and this one is very interesting. It's very interesting. So let me tell you the complexity first. So the average time complexity for shell sort is very special as order n log square n, or order n five-fourth. So it's a very special algorithm with very special complexity. And in the best case, it will be order n log n. And in the worst case, it's order n log n squared. So you may be wondering how does this shell sort works? So it works in a very interesting way. So can the students in the back see I writing here?
Yeah.
Okay, cool. So let me see. So if we are sorting 1, 3, 2, 4, 6, 5, 8, 7, 10. Okay. So the idea of shell sort is that we are having dynamic steps for each path. So for the path 1. For path 1, we are only comparing AI with AI plus n divided by 2. So that is, we only compare 1 and 5, so we keep them, 3 and 8, 2 and 7, etc. And in path 2, we may only compare AI and AI plus n over 3. And in path k, whatever, in the last, we will compare AI and AI plus 1. So by several passes, and in each pass, we are shrinking the steps between the numbers. That is actually, so actually we are getting it partially sorted again and again. Then, after several passes, it will be sorted at the end. So that's how shell sort works, and we will use the video later to show you how it works exactly. So we can call it the new algorithm for this course. So that's the 9 typical sorting algorithms we are introducing in this set of 4 lectures of sorting algorithms. Any questions are welcome.
So is the algorithm called shell sort because the paths look like shell or something like that?
I am not sure actually. I think it's more possible to be just the name of the inventor.
Okay.
Yeah. If you want to invent some interesting sorting algorithm by your own, we can call it Sicong sort. It's fine. Yeah. So yeah. Any other questions about these sorting algorithms? We will also have the they cover in the problem sets homework and the programming coding homeworks.